Our first speaker is Mr. Romulo Broas. He is currently a PhD candidate in systems engineering at the Stevens Institute of Technology. His areas of interests are in modular systems, modeling, simulation, and antenna technologies. He holds a Bachelor of Science in Physics from the University of California at Berkeley, a Master's of Science in Electrical Engineering from UCLA, and a Master of Science in Systems Engineering from the Johns Hopkins University. Romulo is currently a SERC Fellow and will be presenting his work, Applying Search Optimization Techniques in the Incorporation of New Technologies and Innovations in Modular System Upgrades. Romulo, with that, I turn it over to you.
Thank you, Kara. So my talk today will have the following agenda. I will first discuss modularity, introduce it, kind of glance over my literature survey, and then go into the research statement, and then get into the meat of the research, applying systems thinking to modular system upgrades, and then discuss optimization techniques in a preliminary model, and then strategy, and then this critical value that I have defined to be called M sub C, and then I'd like to conclude my talk. All right, so what is modularity? Well, there are arguments that say that modularity has been part of the human complex reasoning since the very beginning. Humans have broken down complicated concepts into smaller parts to understand it, and then likewise we have taken building blocks and then made them more complex. And formal definitions abound in the literature. So there's we can easily do a search in the literature, and you can see many different definitions of modularity. Today, modularity is used extensively to achieve mass production, to build and understand complex systems, and to integrate robustness into designs. I did an extensive literature survey on what is out there regarding modularity, and you can kind of summarize it using this diagram here. There's the very complex mathematical theory that goes over set theory, something called the completeness theorem, the loss theorem, and then gradually you'll see a lot of papers where they apply modularity to theoretical systems using game theory, agile processes, and then you can see very practical systems that incorporate modularity. Things like the PC, the Legos, right? And those are very modular systems. And then there's extensive literature about arguments against modularity. Cell phones, for example, are not very modular, and Apple computers are not very modular. And then now, there are a set of papers that I investigated that talk about when to upgrade and the role of new technologies. Okay, so let's. I won't hit all of these topics, but let's just hit some highlights. First, modularity is not a binary attribute. You can't say a system is modular or not modular. It's not black and white. Instead, there are degrees of modularity that is determined by the coupling between the components. And automobiles are perfect examples, right? You have one case of cars like the Indy 500 race cars that are not very modular at all. They're very specialized, very integrated, almost no modularity, very few produced, very expensive. And then there are very modular cars that basically they're cheap. You can interchange parts, and then but most cars are somewhere in between, right? They do have modular parts. You can go to AutoZone or Kragen and get parts there that can be that's also applicable to other cars. But there are uniqueness in each car that makes them the particular car that it is, the Toyota Sienna or the whatever car you have. An example where modularity really came to the forefront is just back in January, where China, in response to the COVID-19 pandemic, built 2 hospitals in 2 weeks, 2 huge hospitals, and then just a couple months later they tore it down. So okay. So There's extensive literature on very modular systems. The Lego, it's classic, right? You can from these building blocks, from these you can interlock them and build, cars. Yes, uh, I can provide people documentation on the literature survey that I've done. My research, however, concerns, given the choice of many innovations and technologies, which one should be chosen in a modular system, right? So here's a scenario: consider a company doing research and development to improve a particular module. An innovation has been made. Someone progresses the technology. Question is, should the company integrate the new technology, or and upgrade the module, or should it wait for further progress? Right? What are the optimal conditions? Okay, so here's a quick diagram. Right, as you can see, the different topics I have explored in the literature, and all is converging on my research topic, which is developing an analytical framework in which technology to employ, right? The decision making process to evaluate which technology or innovation to implement amid many options. Okay, now we move on to the motivation and research statement, right? So modular systems are upgraded to the incorporation of new technologies or innovations is a complex process. There's stakeholders involved. There are various with people of various interests. The question is, what will govern them? I'm proposing that first we apply systems thinking of stakeholders, shaping forces, concept Tegan, and systemigram analyses, and then using an optimization technique to see what was the best strategy. Okay, let's dive into this applying systems thinking to modular system upgrades. So upgrading modular systems, right? Which technology or innovations to be incorporated, and then we can use thinking concepts of stakeholders, shaping forces, concept Tegan, and systemigram analyses to see what are the critical factors. And what emerges from this, and we will see this in the diagrams that follow, is the central role of the systems engineer in balancing various stakeholder interests. Okay, stakeholders are key individuals who are affected, impacted, interested, or involved in some fashion with the modular system upgrade, and you can identify these key ones. Of course, the systems engineer, program manager, innovator, the person who develops new technology or innovation. There's the company, there's the customer, and of course, there's competitors. We analyze the shaping forces. They are overarching themes that systematically create and mold modular systems throughout time. And in a modular system, the dominant shaping force is the modular design, right? And there are other shaping forces, however, and they are the new technologies and innovations that are coming down the pipe through a company's R&D, right? Okay, concept Tegan analysis. So this is the application of systems thinking to understand complexity, and you'll see in the following charts that I focus on five analysis concepts, five concept Tegan analysis concepts to understand the intricacies between modular system upgrades and the interplay between various stakeholders when upgrades happen. The first one, concept Tegan analysis number one, is hierarchy, openness, and emergence. So here from this diagram, you could see new technologies and innovations are usually incorporated at the parts level, right? And the parts themselves have relationships between them, defined formally as interfaces, right? And then the modules themselves are connected through interfaces, and systems have interoperability to become the system of systems. So this is kind of showing the hierarchy that's involved. If we examine the interior boundary, interior, exterior, this is concept Tegan analysis number two. You'll see that there are different levels of boundaries. There are boundaries between modules, right? You can see a hypothetical system here where there's just four modules, and they're connected by interfaces, and there are weak interfaces showed by these dotted dotted lines, and the interfaces themselves have a directionality, right? You can see module B is a direct input to module A, and then module A has a heavy input to module C, but module C has a weak output that will govern module A, and this is complex feedback loop usually in the system. But there's a boundary also between the user and the customer, right? And then there's a boundary between the system and its environment. Wholes, parts, relationships, Causal analysis number 3. The whole is the system, the parts are the different modules, and the relationship is basically the between the parts and the modules are the interfaces. Causal analysis number 4. Input outputs transformations. Here you could see a schematic of the actual upgrade, right? There's the process of putting the upgraded module, integrating it into the system. And then this is the actual structure, the system with the different modules and their interfaces. And then the output here is improved performance, cost savings, easier, more rapid manufacturing. And this here all converges upon the goal of better system alignment to customer needs. All right. Concept analysis number 4. Structure, function, process structure, function. Again, this is similar to what I mentioned. The process is first implementing the new technology or innovation to upgrade a module. The structure is a system. The function is improved performance. This is a busy chart. This is a systemigram analysis that shows the interplay between the various stakeholders, right? And you can see just almost at the center of it all is the systems engineer, right? There's a system. It's divided into modules, and the modules are integrated into the system. But the system engineer kind of has a role of determining which module gets upgraded, such that it's integrated to the upgraded system, right? But the system engineer takes inputs from the technologists and the innovators who develop and create these new technologies, but also he's constrained by the program manager who imposes budget, schedule, and schedule requirements, and also there's the system engineer is also influenced by the customer and the competition that the customer imposes. Here, this is a key diagram where we see the causal loop analysis, right? So you can see this started at the center. New technologies or innovations, right, are developed. So there's a valve here. So the system engineer, kind of determines which new technology or innovations to incorporate. And there are reasons why he would want to open that valve all the way and let every new technology that pops up incorporate that into the system, or he wants to kind of tighten that. So the positive means a positive correlation. Okay, so if he lets the new technology and innovation get incorporated, right? You have modular upgrades, you have a new system, customer needs are met, there's going to be an increase in customer and market saturation, but that has a negative feedback on sales, especially this customer and market saturation. And increasing modular upgrades, all right, increases imitations and substitutes, and that, of course, has a negative impact on sales as well. So increase in sales attracts competitors. Increase your imitation and substitutes, and then that also decreases your sales. So there's a complex feedback loop here, something that I will investigate further. But this is just a big picture diagram of a very complex loop. All right. So I'd just like to just big picture applying systems thinking in modular concepts in modular systems. I'd like to quickly summarize it. Okay. The central role of the system engineer was better defined, right, when upgrading modular systems through the incorporation of new technologies or innovations. And then By balancing various risks, opportunities, and stakeholder interests, it is the system engineer that dictates the amount and the frequency of the new technologies or innovations that are incorporated. Okay. Optimization applied to a modular system, a preliminary model. All right. So to explore this model, uh, we need to define a few variables. So let M be defined as a characteristic of a module. So this could be a general trait of a module. It could be a performance parameter, market advantage that a module proposes, or any other feature. It can be attributed to a particular module. It could be the amount of losses a module has. Call it 5 dB. Um, and then we could say then that you could have a set of modular attribute metrics, call it MAM, right? Such that you have a set of these, right? Depending on the particular modular design that you have, right? And of course, this M has to be a real number because it is a measure. It needs to be measurable. It must be measurable. Okay, so this M maps to something called S, and S is a characteristic of a system, right? And so you can see there's a function here. The M produces a characteristic of the system. So M is a function of S, and so the modular trait M produces the system performance metric S, and S just like M is a set. There's a set that can be defined for SAM, which is the um, system attribute metric, and just like M, S, SAM needs to be measurable. All right, we'll go over this in more detail. So here's the decision, the diagram, the decision to upgrade a module. Is this a hypothetical case where you have a system with four modules, module A, B, C, and D. For this particular case, the module at hand is module B, right? And module B has there could be four modular upgrades for module B, right? um, uh, they're denoted as M1, M2, M3, and 4. You could think of it as modules with different loss characteristics, right? So let's say M2 matures. M2, is the one that's now ready to be incorporated into the system. Here we go. Does the system engineer incorporate that that module into the? He has a decision: is he incorporated the system or not? If not, he waits for another upgraded module, namely M1, M3, and M4. But if yes, he will put that M2 there, right? If you look at the flow diagram, okay, of the decision to upgrade a module, this is what we can see. Innovators, they develop new technology or innovations. So there'll be a distribution of new technologies or innovations, right? That's the set of MAM, module attribute metrics, and then you have improved features incorporated into a module. Engineer evaluates the improved module. Does he accept it or not? If yes, he integrates it into the system, and then he gets the associated system attribute associated with that new upgraded module, right? He yields it. If not, the integrated module is rejected, not integrated into the system, right? And then he waits for other improved modules. Okay,
Romulo, we have about 5 minutes left.
Okay, thank you. So here's the optimization strategy. Okay, optimization strategy is this. In summary, it's a combination of two approaches. The no upgrades approach. The system engineer said, you know what, I will never upgrade. So what does he get from there? This is it. Okay, no matter what modular characteristic there is, he will always yield the same system performance. SOD stands for default, system default performance. he will always the system performance will never increase. It'll always be constant. The other extreme is whatever comes in, I will upgrade it, right? And so if we assume there's, and we assume there's, this is key. If we assume it's a linear correspondence between modular improvement and system performance, right? I'm assuming for now, for simplicity's sake, it's a linear, it's a linear relationship. The complicated ones where the shape is asymptote or plateaus or Poisson distributions, that's part of the research that I'm working on. But if we assume it's linear, here's what we get: just a y equals x line. The for every system for every module attribute, you will yield the corresponding system performance. The hybrid approach, though, is this: you combine the two and you get the maximum, right? Such that you have a particular parameter, m sub c, such that for every module with performance less than m sub c, you say, you know what, I'm not going to upgrade. But for every module presented that is greater than m sub c, yes, I will upgrade and I will get the corresponding system performance. So clearly, m sub c is the critical value, right? So for m less than m sub c, no upgrade approach yields the default performance. For m greater than c, you upgrade. So in general, what you're seeing is, if you want to do the optimized strategy, you define it as omega. You don't upgrade for less than m sub c. You always upgrade for greater than m sub c. And so let's see how this m sub c, things that will influence this m sub c. OFAT, one factor at a time analysis, right? If we decrease the default, you could see m sub c decreases. So if what is inside the module has if you decrease what's inside the module is less, m sub c goes down. And likewise, all right, if you decrease the slope of this line, right, such that what that physically means is you don't for every you don't get the when you increase a modular performance, you don't get a proportional increase in system performance. If you decrease that, then m sub c increases. So what we see is, just looking at OFAT, is the slope. If you increase the slope, m sub c should decrease. If you decrease the slope, m sub c increases, and then you have corresponding relationship with S sub d, right? Again, examining this critical value m sub c that will determine when a parameter that will help the system engineer decide when to upgrade or not. Conclusion. This research focuses on a systems engineering approach to incorporate new technologies or innovations in modular system upgrades. Right? We talked about stakeholder shaping forces, Conceptigan, Systemigram Analysis, and then a preliminary model for incorporating search optimization techniques proposed. It's preliminary because the line is a linear line, but again, that does not need to be linear. Most upgrades, the relationship can be usually a Poisson distribution. But for now, we're using linear lines, right? Moving forward, okay, we want to examine variables that shift the parameter m sub c will be explored, right? Because m sub c is the point of reference for the system engineer on whether to upgrade a module or not. And then real life examples, applications of the optimization model will be performed. Okay, thank you everyone for your time.